Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Leonhard Euler's mechanics, published in 1736, marks a watershed moment in the history of physics. It represents a decisive shift from the largely geometric methods of Isaac Newton's Principia to a more generalized algebraic and analytical approach, thereby laying the cornerstone for what is now known as analytical mechanics. Prior to Euler, mechanics was primarily regarded through a geometric lens. Newton, despite inventing calculus, couched his arguments in geometric terms, a style that, while rigorous, possessed inherent limitations in tackling increasingly complex mechanical systems. Euler recognized this constraint and embarked on a mission to forge a more flexible and universally applicable method for analyzing motion. Euler's central aim in mechanics involved developing a system where the laws of motion expressed themselves through algebraic equations, particularly differential equations. This contrasted sharply with the geometric demonstrations prevalent in earlier works. The power of this approach lies in its generality. Geometric arguments often proved unwieldy when dealing with intricate scenarios, such as motion in resisting mediums or under variable forces. Euler's analytical framework, however, provided a consistent and algorithmic procedure for addressing a wide array of mechanical problems. The bedrock of Euler's analytical mechanics rests upon his formulation of Newton's laws using calculus. He expressed these laws as differential equations, allowing for precise mathematical description of the instantaneous state of a moving body. This was a radical departure from Newton's geometric approach, where forces were often treated as impulses acting over infinitesimally small intervals. Euler, in contrast, conceptualized force as a vector quantity, defining it through its components along orthogonal axes. This innovation proved essential for handling forces acting in three-dimensional space. Volume 1 of mechanics focuses primarily on the motion of point masses. Euler meticulously examines various scenarios, including projectile motion under the influence of gravity. He derives equations describing the trajectory of a projectile, accounting for air resistance and variations in gravitational strength. These analyses showcase the power of his analytical methods, allowing for the precise calculation of motion in situations that would prove intractable using purely geometric techniques. For example, Euler derived equations to model projectile motion where the gravitational force is allowed to vary as an arbitrary function of altitude. He formulated an approach to solve these complex problems, while introducing integrating factors in the differential equations, a technique widely adopted to determine solutions for these problems. A close examination of Euler's treatment of motion in resisting mediums reveals the brilliance of his approach. He formulates differential equations that describe the dynamics of a body moving through a fluid, considering the drag force as a function of velocity. This allows for the calculation of terminal velocity and the analysis of motion under complex resistor forces. Moreover, Euler tackled problems where the resistance force was proportional to powers of the velocity, which was groundbreaking during his time. Although some solutions were intractable analytically, Euler's formulation allowed him to apply numerical methods, providing accurate approximations. While Newton's Principia undoubtedly served as a touchstone for Euler, the latter sought to transcend the limitations of its geometric framework. Newton's profound insights into gravity and motion provided the foundation, but Euler aimed to express these insights in a more malleable algebraic language. This transformation allows for generalization and automation. Euler's work can be viewed as a systematic formalization of Newton's ideas, rendering them amenable to the tools of calculus and analysis. He accomplished this by converting Newton's geometric proofs into algebraic expressions, thus making them easier to manipulate and extend to novel theoretical constructs. In essence, Euler's mechanics transcends a mere statement of Newtonian physics. It inaugurates a new era in the study of mechanics. By recasting the fundamental principles in the language of calculus and differential equations, Euler provided a powerful and versatile framework for analyzing motion. This framework would profoundly influence subsequent generations of physicists and engineers, paving the way for Lagrangian and Hamiltonian mechanics, as well as modern approaches to dynamics and control theory. The significance of this initial volume lies in its establishment of these core principles that would find even greater expression and application in the second volume of mechanics. The subsequent discourse will venture into the depths of the second volume of mechanics, a volume that grapples with a considerably intricate realm of rigid body dynamics. The unveiling of Euler's conceptualization of principal axes of inertia and the genesis of the renowned Euler equations for rotational motion will receive scrutiny. Additionally, we intend to illuminate the far-reaching implications of mechanics on the epochs that followed, accentuating its pivotal role in shaping Lagrangian mechanics. Hamiltonian mechanics, and its unforeseen contributions to the evolution of tensor analysis and differential geometry, his profound impact continues to resonate throughout modern engineering and physics, marking it as a monumental contribution to the annals of scientific intellect. The second volume of Euler's mechanics ascends into the labyrinthine complexities of rigid body dynamics, a domain where objects possess spatial extent and resist deformation. This book marks a pivotal departure from particle mechanics, venturing into a world requiring novel mathematical tools and physical insights. Here, Euler introduces the concept of principal axes of inertia. These axes represent a set of orthogonal directions fixed within a rigid body, about which the body's moment inertia assumes its extreme values, either maximum or minimum. The existence and properties of these axes dramatically simplify the analysis of rotational motion, transforming what would otherwise be an intractable problem into a manageable form. Euler's derivation of what are now universally known as the Euler equations for rotational motion stands as a towering achievement. These equations, expressed in a body-fixed reference frame aligned with the principal axes, provide a direct relationship between the applied torques and the angular acceleration of the rigid body. They are differential equations which, when solved for specific initial conditions and applied torques, yield the complete rotational motion of the body. The elegance of these equations stems from their ability to capture the intricate interplay between inertia, angular velocity, and external forces, all within a concise mathematical frame. The mathematical techniques Euler deployed in mechanics are noteworthy. He deftly employed orthogonal transformations, mathematical operations that preserve lengths and angles, to describe the orientation of rigid bodies within space. These transformations, expressed as matrices, allow for a seamless conversion between different coordinate systems, enabling Euler to analyze motion from various perspectives. He used these transformations to relate the angular velocity of the rigid body in inertial space to its angular velocity in the body-fixed frame, a relationship that lies at the heart of the Euler equations. Furthermore, Euler's mastery of calculus, particularly differential equations, allowed him to formulate and solve the equations of motion for rigid bodies under a variety of conditions. Volume 2 of Mechanics contains numerous examples that illustrate the power and utility of Euler's approach. His analysis of the motion of a spinning top serves as a classic example. By applying the Euler equations, he derived equations describing the precession and nutation of the top, phenomena that had perplexed scientists for centuries. He also investigated the stability of rotating objects, determining the conditions under which a rotating body would maintain its orientation and resist external disturbances. These analyses revealed the surprising stability of rotation about the axis of maximum moment of inertia, a principle with far-reaching implications for the design of rotating machinery and spacecraft. Despite its brilliance, Euler's approach in mechanics possessed limitations. His focus remained primarily on analytical solutions, which were obtainable only for relatively simple cases. The complexity of the equations often precluded the derivation of closed-form solutions for more realistic scenarios. Moreover, Euler's treatment of constraints, particularly those imposed by joints and linkages, lacked the generality and sophistication found in later formulations. Subsequent physicists and mathematicians built upon Euler's foundation, addressing its limitations and extending its scope. Joseph Louis Lagrange, building directly on Euler's work, developed Lagrangian mechanics, a more general and powerful approach to dynamics. Lagrangian mechanics employs the concept of generalized coordinates and the principle of virtual work, providing a systematic method for deriving the equations of motion for complex systems, with or without constraints. Simon Denis Poisson subsequently developed Hamiltonian mechanics, reformulating the Lagrangian equations into a canonical form, which paved the way for quantum mechanics through the study of Poisson brackets. These developments directly emanated from the groundwork laid by Euler in mechanics. Furthermore, the concepts and techniques introduced in mechanics spurred the development of tensor analysis and differential geometry, mathematical tools that would be essential for understanding Einstein's theory of general relativity. The generalization of the moment of inertia to the inertia tensor, a mathematical object that captures the distribution of mass within a rigid body, required the development of new mathematical formalisms. These formalisms eventually evolved into the tensor calculus, which provides a powerful framework for describing physical quantities that transform in complex ways under changes of coordinates. In retrospect, Euler's mechanics stands as a transformative work that fundamentally reshaped the landscape of classical mechanics. His introduction of principal axes of inertia, his derivation of the Euler equations, and his skillful application of mathematical techniques paved the way for modern approaches to dynamics, control theory, and robotics. The precise analytical methods he pioneered continue to be employed in contemporary engineering and physics. providing engineers and scientists with the tools needed to design and analyze complex mechanical systems. Euler's legacy endures, a testament to the profound impact of his intellectual contributions.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.